Hello, everybody. This is Michael. In this video, we will talking about ADC AD7819. So we will implement Verilog code control the ADC and also implement the virtual devices for the ADC for simulation. So it's very interesting things. But before we do this, we should know some basic knowledge about the devices. So the information what we can get is from the, of course, from the datasheet. So there's lots of information in the datasheet. What we should care, what we should know. So we start from here now. Okay. So this is some basic information we should know. First, we should know the devices for what? Of course, it is an ADC. It's an analog to a digital convert. So this is ADC, the first thing we should know. The second thing, so it is 8-bit, okay. So this is 8-bit ADC. The third thing, so it's 1.7 volt to 5.5 volt. So this is input voltage. So it means it can compatible with 3.3 and 5 power supply. So for the microcontroller system or for the FPGA system, this 2 voltage is a very normal power supply voltage. So it can use for both of them. Okay. So the next thing is the analog input range. Okay. The analog input range. So the analog input range is 0 volt to the reference voltage. The reference voltage is here. The analog input is here from this pin input. And this is a power supply. The power supply is from 1.7 to 5.5. So this is power supply. Okay. This is 8-bit data output. Okay, this is for 8-bit data output. Let's take a look. So we need the 5 things. The reference input is 1.8 to system to the system power input. 1.2. Sorry. The reference input is 1.2 voltage to the system power supply, which means so you can measure you can measure from 0 to the system power supply range from the analog input. Okay, so this is okay. So these things is it has a power down mode. Okay, so let's take a look here. So it has a very good feature. The ADC has a very good feature. It's power down mode, and it's a single supply option. And the power down mode can significantly reduce the power consumption. So it's very suitable for the battery powered application, like the portable devices. Okay, so this is the device's feature. Okay, this is the function block diagram. Okay, here is the function block diagram. This function block diagram tell you something about the internal structure. So how it will be internal. This is control logic. So this is control pin. So this is 3-state drivers, and this is output pin. Output pin, which means we can connect the data from here. So this is a power supply, and this is power supply. This is ground, and this is reference voltage, and this is measure power, measure voltage in. Okay, so these, okay, next things will be the pin function description. Okay, we go through that. Okay, here is the pin function description. This pin function description is very important. Actually, we can create the black system box. Okay, we can actually create the black system box here. So like we do like this. Okay. So okay. Let's take a look at the first pin. So this is reference input. Okay, reference input, and this is analog input, and this is ground. Okay, this is convert star, and this convert star. So it's an input pin. So we make it like this. Like this is okay. This is negative effect. So convert. This is input pin. Okay, so we make it like this. This is input. Okay, so see next. So CS is chip select. It's a logical input. Very good. It is also an input. Okay, that is also an input pin. CS. Okay. Next. Okay, next. So this is a read pin. This is also a logical input. Very good. So we get another pin. It's like read. Okay. So this is another pin. Next. Busy. This is a logical out. Very good. We get it here. So this is logical out. Okay. So this is state. This is state bit. These outers are 3-state, and this is TLL compatible. Okay, let's make it like this. DB, okay, 27, like this. Okay, so this is also output, and this is VDD. Okay, so that's it. So we can make by this way. So we already can make the system blocks like this. As you know from the previous video, the system black box is very important for us to create create the Verilog status machine, and to create the Verilog code. Very important for the programming. Okay, so this is pin function description. Okay, the next things will be the ADC transfer function. Means how to get your ADC value, voltage value, calculated by the digital value. Calculate through the digital value. Okay, this is it is in page A. Okay, page A. go to page A. Okay, it's here. So you will see the output coding of the ADC is straight binary. Very good. It's a binary coding. So it means, so you can see from 0 to 256. So this is the maximum. This is minimum. So it measures from 0 to reference voltage. So reference voltage divided equally divided 256, and then you will get the digital value here. So this is multiple. So you will get the measure the input voltage. So this is the formula you can calculate your input voltage. Okay. The next thing is power up timers. Okay, let's take a look. So this is the power up time. For the power up time, because the very good feature of the ADC, it can power down, and so save time. So how it power up, power down, power up is a critical thing for the ADC. It's the first step. It's the first step for the chip to work. Of course, you need to power up the chip, then can convert. Otherwise, if you cannot power up, it cannot work at all. How it power up? So this is the description. But it's better to take a look here. Yeah, it's better to take a look here. The description tell us, okay, it has 1.5 microsecond power up time, and it will trigger by a rise edge on internal generate to generate the signal. And you will see here, okay, from here, this is rise edge, this is X, and this is outside external, this is external convert signal, this is internal convert signal. So the internal signal will be this one. This one is internal signal. This is external signal. This is the pin, which will be which is this pin. Okay, so this pin. This is the pin. It means when we have a rise edge, this edge, it will trigger the internal convert signal also, and in the internal signal will keep 1.5 microsecond, and then added OR gate. So it's here 1.5 microsecond. This is external. So okay, so we'll have two situations. One situation is like external, the high level keep less than 1.5 microsecond. Another situation is greater than 1.5 microsecond. So no matter it is less, okay, so you will see here. So this is okay. So no matter it's less or great, when it is less, so it's when it is less, let's say here, when it is less, so this will be 0, and this will be still keep 1, okay. Or we can get Yeah, we can get a status. Actually, we can get a status table here. And let's say this is external. This is external convert. Okay, this is external convert. Then this is internal convert. So let's take a look here. Think one thing. So one thing is when the okay, less than 1.5 microsecond, the external go down. It means 0, but the internal will still keep 1, and then the output here will still keep 1. Why? Because you can see here, this is OR gate. 1 or 0, it will be still 1. So it means we'll keep the ADC keep power. Okay, so let's say equal to 1.5 millisecond. It can be 1, also can be, it can be 0, also can be 1, but this one still will be 1, and then the output will be 1. And the third thing, greater than 1.5 microsecond. So let's this keep 1 and this keep 0, because this one will be only keep 1.5 microseconds. So the output will keep 1. By this way, it will control. By this way, it will control the ADC chip. At least it will have 1.5 microsecond to power up. It keep the timing for the devices have enough time to power up. Okay, this is very interesting, very important for understand the chip power up situation. Okay, so this is power up. Okay, so how we control it? Okay, it has two more to control the chip. Two more. The first one is this one. Okay, the critical, the detailed description is this, is here and here, but the very important one is for the first mode at here, at the busy, this position at the busy follow edge, the external convert must keep high. So if you keep high at this position, and the chip will not power down and will continuously convert. And if you this is the second mode, the mode 2, and if you at this position, the busy position keep low, and then the chip will go power down more and save save the power for the better battery performance, for the better. Okay, so that's it. So this is more 1 and more 2, and this is has one thing needed to understand is the KSBS. So you will see here for the more 1, it can keep the data rate like 100 KSPS. What's mean about the KSPS? So it's kilo samples per second, thousands of samples per second. It means in 1 second you can get a 100. In 1 second you can get 100,000 samples. The convert rate, the sample rate is very is kind of good. It's very good. Okay. So the next things how to get the data, how to get the output data. Okay. So we have 2 more to control the chip. So how to fetch the data out. So after the busy, the follow edge, we need control the CS and read as a low, and then begin to read the data. There is a timing. There is a required timing to control. So this is the portable timing. So in the future, Verilog coding, we will address this detailedly in the virtual devices programming. This timing is very important. Okay, so this timing is very important. Okay, the last thing is microprocessor interface. Okay, so this is a microprocessor interface for the ADC. So it's a very typical interface, CS and read and interrupter. This is interrupter, this is data. So this is a microcontroller and something like this. Okay, basically from the data sheet we can get the information like this, very important information, but and it's good enough. It's enough for our coding and control the ADC chip. This ADC chip is very simple but very useful, and the ADC, and we will use the Verilog to create virtual devices for it, and also the control devices, control flow for the devices. Okay, that's it for this video. Thank you. This is Michael, and I hope you will like it and support us, subscribe us. Thank you again.